Hi everyone. In this talk on the sensors theme, I'm going to be discussing our work on hot carrier photodetection. In any semiconductor photodetector, we usually construct a PIN junction or a PN junction. Light incident on the semiconductor can excite electron hole pairs if the photon energy exceeds the bandgap energy, and these electrons and holes can be taken away to generate a photocurrent by the built-in field of the PN structure. However, we need not be limited by the bandgap of the semiconductor. For instance, consider the Schottky barrier structure. We already know from earlier talks today that shining light on a metal can generate hot electrons, and potentially these hot electrons can beat this barrier. The difference here is that we're not limited by the properties of a single material and the bandgap of the semiconductor, but the combination of materials. If we can find the combination where this barrier is low enough, we can achieve photodetection below the bandgap of the working semiconductor. This idea is not particularly new. Back in the 1980s, metal silicides were used to extend the range of silicon photodetectors out to about 5 microns. Indeed, this shows a picture from a paper in 1980 of a 256 pixel array based on platinum silicide Schottky detectors. So recently, this idea has been resurrected in the era of plasmonics. Initially, this seminal work in Science magazine showed responsivities of 10 to the minus 6 amps per watt, which is not particularly efficient. But more recently, the responsivities have been improved by many orders of magnitude. And this is getting to the point where commercial relevance is a prospect. So I want to show you one work on Schottky barrier detectors. These detectors are quite distinct in two ways. Firstly, they use a different type of metal, titanium nitride. And titanium nitride has a surface oxide layer, titania, and this proves to be quite significant in the operation of these devices. Secondly, this is an extremely simple device. It is nothing more than planar layers. We illuminate from the substrate side. No photons above the bandgap make it to the device, so everything detected is sub-bandgap. This shows you a picture of responsivity versus wavelength. This shows you the bandgap energy at the edge here, about 1100. And later on, we're going to benchmark this against other devices from the literature at 1250. This is our benchmarking wavelength, where the responsivity is a milliamp per watt. It's pertinent to point out here the distinct response of the gold silicon structure. This is the typical technology exploited in the literature, and the titanium nitride silicon structure, which is the blue line. And this enhancement in response, we believe it's down to the titania layer. Of course, titania is a known photocatalyst, and that's been identified in earlier work. In another piece of work, we're not using a Schottky barrier, but we are using hot electrons, and this is the inhomogeneous distribution of hot electrons. So this device is based on graphene. Graphene is the working semiconductor here, but we could use other semiconductors as well. These two electrodes, one is a hot electrode. This is the one decorated with antennas, and this will generate hot electrons. And the other antenna is effectively a cold electrode. So what do we mean by hot electrons here? When we illuminate the antennas, what happens is that we excite electrons in the graphene, and these want to diffuse away because they're highly localized regions where they're being excited. Okay, and this is through the Seebeck effect. And this turns out to be the dominant effect in these devices. So this red line shows you the response without the antennas. This shows you the response with them. And the responsivity of this device is extremely competitive when it comes to other graphene-based photodetectors. It's worthwhile pointing out that the Seebeck effect can be stronger in doped semiconductors, and this is a research route for the future. The other reason I bring up this photodetector is that we've measured directly the photo response time of these detectors. It turns out to be picosecond scale, in this case 1 to 2 picoseconds. This also goes for any hot electron photodetector, where hot electrons have these lifetimes which are extremely fast. Finally, for some benchmarking. So we benchmarked these devices at the wavelength of 1250. This is where silicon technology just doesn't work anymore. And all of these devices from the literature have benchmarked to the same wavelength. It's worthwhile pointing out that InGaAs technology, with its lower bandgap, can detect wavelengths in this range with responsivities which are close to perfect. That's just less than a milliamp per watt. So all of these studies show a milliamp per watt responsivity. One of them here gets up to almost 10 milliamps per watt. We believe that this titanium nitride technology could be able to push to this kind of range. Indeed, under bias, we're already in the 10 milliamp per watt range. So what are the advantages? Clearly, there is technology with better efficiency, but here we need to point out the wavelength independence if we can find the right materials, the cheap materials available and the cheap fabrication involved in making these devices, and finally, the ultra-fast response times. I'm going to leave you with some discussion points. What about cheap silicon photodetector technology, extending the wavelength range, perhaps using infrared detector arrays based on silicon to boost it out into the infrared, mid and long infrared? What about fast photodetection? What are the applications for exploiting a response time of 2 picoseconds or so? And finally, what are the target responsivities or detectivities required to make a commercial success of these devices? Thank you.
I would like to introduce a new type of a gas sensor based on plasmonic nanostructures, in particular a nanostructured platform based on gold nanorod arrays. The size of each nanorod is few tenths of nanometers. The distance between them also few tenths of nanometers, but they can be fabricated over microscopic centimeter size area. If they are illuminated with light, hot electrons can be excited in the nanorods and they can improve sensitivity, selectivity, and time response of the sensors. The nanorods can be functionalized to sense different types of gases. We demonstrated sensing of hydrogen, oxygen, humidity, important for various chemical industry. In particular, I will focus on hydrogen sensing, which is important in chemical industries, as well as since hydrogen is one of the most important clean fuels for zero-emission economy. Plasmonics has been used in sensing application for a very long time. And an excellent example of this is this biocore instrument based on surface plasmon resonance. It is widely used in pharmaceutical industry, chemistry, biochemistry, whenever you need to sense molecules or molecular interactions. The sensing chip in this case, just a smooth, thin gold film, but is very expensive. In the past, we tried to improve sensitivity of this type of sensors using our nanorod arrays. And indeed, we demonstrated that sensitivity can be improved more than 2 orders of magnitude than for smooth gold film. Unfortunately, in this case, this sensor chip became too sensitive to everything, to temperature, to vibration, and with such sensitivity, nobody wants to use it. In order to apply this sensing platform to hydrogen sensing, the nanorods are functionalized with a very thin palladium shell. If we shine light onto this sensing chip, we can observe transmitted or reflected light if hydrogen is not there. However, even if a small quantity of hydrogen is present, it starts interacting with palladium, changes optical properties of the nanostructure, and transmission become much, much smaller. We call it seeing hydrogen with a naked eye. In this way, the sensors allow to sense hydrogen gas without the need of any electric connection in the potential hydrogen environment, which make it safer than conventional electric sensors. The sensing chip can be fabricated in a scalable and inexpensive way, as we are using purely electrochemical approaches. We have recently started fabricating the sensing chips on 4-inch wafers. The cost of one nanostructured wafer is around £1, if we not count cost of the wafer itself. We can design the operating wavelengths by changing the geometrical parameters of the nanorods, and we can design sensors that can work in visible or infrared light, whatever application would require. Importantly, the plasmonic nature of the sensor not only provides extremely high sensitivity of optical response to the presence of hydrogen, but it also helps to improve interaction of hydrogen molecules with palladium. The nanorods provide a source of hot electrons, and this facilitates the incorporation of hydrogen in palladium. The sensor can be realized with optical interrogation like this. So no electric contacts are needed in the monitored atmosphere. In principle, you can place it on the moon and interrogate from the Earth, if you like. Alternatively, you can furnish it with a cheap LED and photodetector like this and use it in usual way as conventional electric sensors. However, in contrast to conventional electric hydrogen sensors, no current flow take place in this case, and sensing chip is not poisoned by other gases which may be present in the environment. I will briefly show you the demonstration that we exhibited in one of the SPAE conferences. So what you see here is a sensing chip, and then it was live demonstration, and then this sensing chip was hooked up to some chemicals which produce hydrogen, and now you see baseline. So now hydrogen is generated. So you see LED sensing chip detector. So you see signal that hydrogen is present. When we stop presence of flow of hydrogen, you immediately now we'll see how sensors is restored back to the baseline. So this concludes my presentation. I just leave you with some questions to think and for future discussion. And thank you very much for your attention.